All right, folks, welcome to our first day of remote learning. So we're going to be talking about exponential functions, which is where we kind of left off when the school is closed. So we're going to be looking at their graphs today. You're going to have an assignment on Desmos. You'll have a week or so to work on it. And then I'm not exactly sure how the grading for that stuff's going to work out quite yet. We're still waiting on some direction from the district and the building. But then like the following Monday, you'll get another assignment, like continuing on with this unit. In class every day, we got the album cover on the title slide there. And obviously we don't have that. However, this came in the mail from me yesterday. It's the Whip record. It's actually from a Seattle band way back in the day. I think the early 90s or something like that. Recorded it back then, and it just now got released. They kind of lost the stuff. It's good though. It's loud. It's a fun rock and roll thing. So if you like those kinds of sounds, definitely check it out. If not, then keep listening to whatever it is that you've been listening to. So let's get started here with the math itself. So we're looking at exponential functions. Now with exponential functions, I hope we see exponent in there and we see function. So function means we're connecting x and y together in some way, shape, or form, where each input gives us one output, and everything's gonna have exponents. And these functions look like this. Y equals 2 to the x is a very nice basic version of it, and we can go up to things like y equals 4 times 3/4 to the x minus 2 plus 7, and that's a slightly uglier version of the same type of function. In fact, in today's Desmos activity, you're going to be figuring out like what does that 4 do to the shape of the graph? What does the x minus 2 do? What does the plus 7 do? What does the 3/4 do to the graph? But before we start looking at the basic graph, we're going to remind ourselves about some basic exponent properties that we need to know. So some basic exponent properties. I hope that we remember that like something like 2 to the 5th simply means 2 times 2 times 2 times 2 times 2, and it's equal to 32. We also need to note the negative exponent properties. So with negative exponents, having b to the negative m power is equal to 1 over b to the mth power. So the base b gets moved to the other side of the fraction, and then the exponent becomes positive. This does rely on the fact, though, that b does not equal 0. So let's look at an example of some numbers. I think that can be a little more helpful. So if we have 3 to the negative 4th power, that is just 1 over 3 to the 4th power. If we have 5 to the negative 2nd power, that is 1 over 5 to the 2nd power. And depending on the context, you might want to simplify this. Like this might be easier to write as 1/25. However, this is 1 over 81, and that might be like a little less helpful to have. It kind of depends on the situation. Our other big exponent property is the 0 exponent property. And the 0 exponent property tells us that your favorite base raised to the 0 power is equal to 1, given that your base is not 0. Again, so if we took 3 to the 0 power, that is equal to 1. If you took 1/2 to the 0 power, that is equal to 1. And those are going to be the basic properties that are going to help us get started with graphing this function. So we actually are going to graph this first one, this y equals 2 to the x. So it's kind of like the parent function. It's the most basic version, I think. So graphing y equals 2 to the x. Well, when in doubt, we should make a table, because tables always work for us. So we're going to have our x values, and we're going to have our y values. And we're going to choose -2, -1, 0, 1, 2. I'm going to do probably more than I need to do here, just to illustrate a couple of points for you. And for our y value then, that means I'm going to substitute these x values all in up here. So we're going to get 2 to the negative 2nd power. And if I look back up here at all my negative exponent properties, that just means it's 1 over 2 to the 2nd power. And that one's simple enough for me to say is 1/4. I'm going to continue on with x equals -1. I get 2 raised to the negative 1st power, which according to my exponent properties is 1 over 2 to the 1st power, which is just 1/2. So far, so good. I'm going to substitute 0 in for x, and I'm going to get 2 to the 0 power equals just 1. That's that 0 exponent property right there. Continuing on, 2 to the first power equals 2, 2 to the second power equals 4, 2 to the third power equals 8, and 2 to the fourth power equals 16. All right, now this is more than enough points for us to graph this. There are a couple of things to point out here. This 0, 1 is the y-intercept. It's when our x value is 0, so it's right on the y-axis. The other big thing I think to note is that our x values increase by 1. This is not uncommon. In fact, I chose these x values because they all increase by 1. But what is interesting is what happens with these y values. To go from a quarter to a half, we multiply by 2. To go from a half to a whole, we multiply by 2. To go from 1 to 2, we multiply by 2. 2 to 4, we multiply by 2. 4 to 8, we multiply by 2. 8 to 16, we multiply by 2. So that means with exponential functions, our y values multiply by the same thing each time. To go from one x to the next. Now that's a little sloppy in my language there. When I say from one x to the next, I mean going up like a full integer value. I'm gonna keep multiplying by 2. If I wanna know what happens when x is 5, I can just multiply that 16 by 2. This is different than how other types of functions go. Linear functions, we add the same amount each time. Our x goes up by 1, so here we're multiplying by 2. And what this does is it makes our graph go very, very quickly. It's gonna start out pretty small, but very, very shortly it's gonna be big. So let's take a look at sketching a graph of this thing. Got -1, -2, 1, 2, 3, 4, 5. Why not? I go up to 16, so why don't we count these things by 2, 4, 6, 8, 10. That's unfortunate, isn't it? It's okay if every point doesn't fit on the graph. Again, these things grow super quickly. And we're going to start plotting these points. So we have -2, 1/4, which is about right there. We got -1, 1/2. So over to -1 on the x, up to about 1/2 on the y. 0, 1, there's my y-intercept. 1, 2, 2, 4, 3, 8, and then 4, 16 goes off the graph. So let's connect these things with a smooth curve. So smooth. Now there's two things to note here. We have a flat tail on one end. On this end, we have rapid growth. This continues to grow really, really rapidly. If we drew like a straight line segment between all these points, they would get steeper and steeper and steeper. That's because exponential things grow very, very quickly. When we are out of school right now for this COVID-19 business, diseases tend to spread exponentially, where if you give it to 2 other people, then they all give it to 2 other people, it grows exponentially, which is why things start out being like, oh, it's not that bad, we only have 15 cases, maybe it'll go down to 0 soon, but next thing you know, we have hundreds of thousands of cases. These things grow very, very quickly, and it can seem like not a bad situation at first, and then things get, pretty drastic. Unless it's like your money that we're modeling, in which case it's not a bad thing to have it grow quickly. And this here is showing us exponential growth. And it's growth because it's getting bigger. We're not going to look at what happens right now, but there is a way to make your function instead look something like this, which would be considered exponential decay. And it has to do with changing one of these numbers to a certain thing. And again, you're going to see how that happens with our Desmos activity. So I think, again, the key things to note about exponential functions are that the y values multiply by the same amount each time. They're flat on one end and go up forever, very, very rapidly on the other end, unless it's decay, in which case it goes up on one side and it flattens out on the other side. That means that our domain is all real numbers. there is not a single real x value that you can plug into this function that's gonna mess up your result. So we can say set of all x values such that x is real. But our range is not quite so nice. Not that it's particularly bad, it's just not everything. This line looks like it flattens out here, and in fact it does flatten out. And it looks like it levels out at 0, and it in fact does. If we look at this table but go backwards, we take 16 and divide by 2 and get 8, divide by 2 and get 4, divide by 2 and get 2, divide by 2 and get 1, divide by 2 and get a half, divide by 2 and get a fourth, divide by 2 and get an eighth, a 16th, a 32nd, a 64th. It's going to keep getting closer and closer to 0 without ever actually crossing 0. So that means that we're going to have the set of all y values such that y is greater than 0. Again, we're going to see that this can change depending on what you change up here in the Desmos activity, but your domain is always going to be the set of all real numbers. I hope that's enough to get you started with your Desmos activity. Please feel free to comment with some of your questions, either on here, on Google Classroom, or send me an email. Miss all of you, and I hope that this works out pretty well. If it's difficult, just know it's the first time that we're trying to do this, and I can make changes. Just give me some feedback about what works well and what doesn't work well. Good luck.